This video is presented by Chuanxiang and Ce Zhang for ECE 542 for Machine Learning Final Project. Our topic is a novel multiple features-based neural network for EEG motor imagery classification. Here is the outline of the slides. EEG is a non-invasive electrophysiological monitoring method to record the electrical activity of the brain. Here we use the EEG capture equipment, the signals processed through signal amplifier to store in the storage devices. The EEG features usually can be observed in temporal domain, frequency domain, and spatial domain. We did the literature research of the conventional machine learning algorithm on the EEG-based MI study. Here is a procedure diagram shows the procedure of the conventional machine learning algorithm. And we also did the neural network learning algorithm research, who is using the feed-forward neural network classification, end-to-end conventional neural network, and the recurrent neural network. However, all of their algorithm is experiencing a relatively low result due to lack of features. So we choose to use the multiple feature-based neural network to provide a more robust result with good accuracy.
I will discuss the proposed algorithm architecture and the experiment result. The proposed algorithm contains three parts: a feed-forward neural network, and a 1D convolutional neural network, and a 2D convolutional neural network. So first part is the CSP-based feed-forward neural network. As shown in this flowchart, the CSP feature dimension is 12 by 1, and the FNN is a 4-layer neural net. To increase the learning speed and efficiency, the learning algorithm is adaptive learning rate optimization. Then next is the ERD-ERS architecture. It is a 1D convolutional neural network. Since the input channels are considered as independent with each other, the kernel size is 1 by 101 and convolve only based on the temporal domain. The learning algorithm is same as the CSP-based neural net. Next is the raw EEG data neural net. Since both the temporal and the spatial are dependent with each other, in this model, 4 convolutional layers are implemented to process the EEG data. 2 of them are spatial kernel, and the other 2 of them are temporal kernels. Next, I will discuss the experiment protocol and the data. The experiment data is an open source data from 2008 BCI computation dataset 2A, and the picture is the experiment flow. The details about the experiment is shown in these slides. Then I will discuss the classification accuracy comparison with our proposed algorithm and other popular algorithm. Our classification accuracy is over 90%, which is much higher than the other state-of-art algorithms. Moreover, the variance of the classification accuracy is among all subjects of the proposed algorithm is the smallest, which means the proposed algorithm is robust and reliable for different kinds of subjects. This result makes sense because we fuse and combine multiple features together. Besides the accuracy, we also compare with the Cohen's-Kappa coefficient. As you can see in the table, our proposed algorithm is also highest in the Kappa value and the lowest in the variance. Next, we analyze the confusion matrix to investigate the classification performance among all classes. First, based on the confusion matrix, we can prove that the testing sample classes are evenly distributed. Moreover, most subject motor imagery events can be successfully detected in all 4 classes. However, for subject 7 and 9, the model tends to misclassify the left and right classes. It is because the threshold we determined is fixed. In conclusion, the proposed algorithm can provide a higher classification accuracy and a more robust classification among all subjects. However, the MFNN still need to be improved, and the potential improvement is listed in the slides.